Welcome to fourth module of Fundamentals of AC Systems. The title is Measurement of Power in Three-Phase Circuits. This module consists the power measurement in AC circuits, various methods for power measurement in three-phase circuits, and 3 wattmeter method for power measurement, 2 wattmeter method for power measurement, and single wattmeter method for power measurement. Next, we are going to discuss the difference between balanced and unbalanced load and power factor conditions, and method of finding reactive volt ampere by using 2 wattmeters, and finding reactive volt ampere by 1 wattmeter method also under balanced condition. And we will discussing the methods of improving power factor and identifying various power correction equipments also. Let us discuss firstly the load conditions, the balanced and unbalanced conditions of a load. It gives a proper idea of total power measurement in this module. So first we are discussing the load conditions in three-phase system. Here load conditions are two types. One is balanced load and the one is unbalanced load. So under balanced condition, all the phases has same voltage magnitude and same current magnitude. That means in this condition we are telling the system is under balanced condition. The balanced load in three-phase system is a condition where all three phases or lines carry same magnitude of voltage and same magnitude of current with evenly spaced 120-degree phase difference. If the load is star connected with neutral as return path, this neutral will carry no current because at the neutral point all the magnitude or algebraic sum of three currents becomes 0 under balanced condition. This is so since vector sum of all three phase currents meeting at common neutral point is 0. So there is absence of neutral current. So VR equal to Vy equal to Vb and IR equal to Iy equal to Ib. All currents are same and all voltages are same in balanced condition. Next, in the unbalanced conditions usually from unsymmetrical loads. Suppose any one phase has more load and other two has less load, means one phase carries more current. When current increases, subsequently the voltage decreases. So unequal current and unequal voltages in three phases. That is where all line voltages are not equal to each other. Suppose any two phase voltages equal and third one is not equal, that also unbalanced. Or three phase voltages are also different value, that is also unbalanced. In the current also three phases carries three different current, means unbalanced. Or two phases carry same current and last one carries different current, that also unbalanced condition. All line currents are also not equal to each other and sum total of these at neutral point is not 0. At this condition, the unbalanced condition, the algebraic sum of three currents are not equal to 0. So there is a neutral current. Load in each phase is different, carrying its own current. Neutral in this case carries the net unbalanced current. So unbalanced current is passing through neutral to earth. So the neutral wire carries the current in the unbalanced condition. The next slide we are discussing the difference between balanced and the unbalanced condition. What we discussed in the earlier slide, the same we are listed here. So under balanced load and under unbalanced load. So first point, under balanced load is all the three phases carry same current. In the unbalanced case, each phases carries different current depending upon load. So different currents. Neutral current is 0. In the unbalanced condition load, neutral current exists. In the balanced load condition, third point is no need neutral wire because there is no neutral current. but in unbalanced load condition neutral wire is must and needs large size because it carries large current also. So no need special attention. In the under balanced condition, no need special attention on the system, but under unbalanced condition needs special attention that one phase is overloaded or two overloaded and other phases under loaded or no load condition. So every second the attention is required in the unbalanced load conditions. So always preferring the balanced load condition in the three-phase system. So this is the difference between balanced and the unbalanced load conditions. So just remember, in the balanced condition all the voltages are equal and currents are equal, but in the unbalanced condition all the three phases carries different voltage and different currents. It's the main points in the balanced and the unbalanced load conditions. So next is power measurement in three-phase circuits. So to measure the power in three-phase circuits, we are using mainly three methods. One is 3 wattmeter method, second one is 2 wattmeter method, and third one is 1 wattmeter method. So in these three methods we are going to find out which is good for power measurement and which has more advantages than other two, etc., and which is convenient for the power measurement for three-phase system, etc. So first we are going to discuss the 3 wattmeter method, later we are going to discuss the 2 wattmeter method, and finally we are discussing 1 wattmeter method. So while discussing these three conditions power measurements, we have to remember every time the balanced condition and unbalanced condition, whether the selected method is measuring or under both conditions. Suppose balanced condition also it gives proper accurate reading, and under unbalanced condition also the selected power measurement method gives the accurate power measurement. So always remember the unbalanced condition and the balanced condition while discussing the methods of power measurement. So first we are going to discuss the 3 wattmeter method. So figure shows the 3 wattmeter method. So in this case it is very simple to calculate because we are using 3 wattmeters. For each phase 1 wattmeter we are going to use. So total power means it is very simple, it is a sum of 3 wattmeters, W1 plus W2 plus W3, that gives total power of the three-phase system. So in this case first we discuss the star connected system. Here W1 connected across the line R and neutral, and W2 connected line Y and the neutral, and W3 connected line B and the neutral. So W1 and W2 and W3 gives the power in R phase, Y phase and B phase. So in this case, suppose this one is under balanced condition, the total power is W1 plus W2 plus W3. Suppose in case of unbalanced condition also, the total power is W1 plus W2 plus W3. Maybe it may carries the different value. Suppose R phase has heavy load, so the W1 shows the more power. Suppose Y phase has very less load, so it shows also very less load, less power. Suppose this one is not connected to any load, so it shows 0. So we will get the total power W1 plus W2 plus W3. Clear? So under balanced and unbalanced condition it works properly and gives total power is very accurately in this 3 wattmeter method. And here the first figure shows in the delta connection how to connect the 3 wattmeters. So each phase getting its own wattmeter. So this one belongs for W1, this one for W2 and W3. So three phase values are getting its own wattmeters. So here also balanced or unbalanced condition it gives values W1 plus W2 plus W3. So under balanced condition, all may be equal values. In the unbalanced condition, all the three wattmeters shows different value, but anyway the total power is gives very accurately. So its advantage is it gives very accurate value and it gives individual power in the phases. That's the main advantage of 3 wattmeter method power measurement in a 3-phase line. But its main disadvantage is it requires more connection and it requires more wattmeter. So we have other two methods. Another second one is 2 wattmeter method and 1 wattmeter method. Comparing that to, it requires one more extra wattmeter and connections also more, 3 wattmeter connections, and in the delta connections it is very difficult. The delta connection, it is very difficult to connect these 3 wattmeters because we have to connect each phase its wattmeter current coil and the pressure coil properly, and we have to make it delta also very properly, or else it won't get the proper output. So this connection is very difficult in the delta case, but in the star connection is no problem, but it gives more connections because 3 wattmeters are required. These are the disadvantages of the 3 wattmeter method power measurement. But advantage is it is very simple. That means W1 plus W2 plus W3 in both balanced and unbalanced condition, it gives more accurate value and will get individual phase power also. These are advantages. So next we are going to discuss the 2 wattmeter method. That is very important. 2 wattmeter method 3-phase power measurement, but under unbalanced load. So in this case we are using only 2 wattmeters to measure the total power in the 3 phases. Here the W1 and W2 connected in the W1 connected R phase, the current coil connected in the R phase, and the pressure coil connected across R and B. Similarly, the W2 connected, the current coil connected, the top one is current coil, the current coil connected across the Y line, and the pressure coil connected Y and B. So from this connection, the current, the W2 is measured the current in the Y phase and the potential difference Y and B. Here W1, the current measures in the R phase and the potential difference in R and B. So we should know the working of the wattmeter. The wattmeter gives the multiplication of the current carries in the current coil and the voltage or potential difference across the potential coil into its cosine of the angle between voltage and current, Vi cos phi. So here the W1 is connected across R and B, so its potential difference is voltage of VRB. VRB is the here voltage, VRB or ERB, anyone, and it measures the current in IR. Clear? So multiplication of the instantaneous values. In the second module we calculated power, the power equal to V into I, instantaneous value of V and the instantaneous value of I. We got the power is Vi cos phi. So multiplication of instantaneous values means this is a power. So here also we are going to multiply the instantaneous values of voltage and the instantaneous values of current. So ERB is the instantaneous value of voltage across the W1, wattmeter 1 is connected, and the current is IR. IR is the current, instantaneous current in the W1 or wattmeter 1. In the W2, the voltage is instantaneous voltage is EYB, and the instantaneous current in the W2 is IY. So multiplication of EYB into instantaneous value of current IY, EYB into IY is the power in the wattmeter. So next what we are going to do means we are adding these two, W1 and W2, that is the total power. Suppose the total power is getting the multiplication of three phases and the phase voltages and its current, means it's a total power. That means ER, instantaneous values of R phase values, ER into IR plus EY into IY plus EB into IB. That means it is the total power. Suppose while doing the derivation, W1 plus W2 gives ER IR plus EY IY plus EB IB, means it is a total power in the form of instantaneous value, but the wattmeter measures its real part. That means it shows the power, means the total three phase power. So next slide we are going to discuss the same. So here instantaneous current through W1 is IR, small I and capital R we denoted, and potential difference across W1 is ERB. So ERB again we elongated, that is ER minus EB, what we did in the third module problems. So ER minus EB is the potential difference across W1. So power read by W1, third line is power read by wattmeter 1 is IR into ER minus EB. W1 is IR, that is a current, into its voltage, instantaneous voltage is ER minus EB. Clear? So similarly the second wattmeter W2. So W2 here the current is IY, instantaneous value is IY, and W2 potential difference is EYB. EYB means Y to B line, so that is EY minus EB. So power reads in W2 means IY into EY minus EB. So it's a power in the W2. Now the total power means W1 plus W2. So W1 is, we written here, W1 is IR into ER minus EB. This is not ER, that is IR. This changes. So IR into ER minus EB plus IY into EY minus EB. So here only IR, not ER. IR into ER minus EB plus IY into EY minus EB equal to, so we are taking IR into inside, so IR into ER, next IR into EB, that is minus EB. So I am writing here, so I am writing here IR into ER minus IR into EB. Similarly the second part is IY into EY plus IY into EY and IY into minus EB, so minus IY into EB. Clear? So here IR ER and IY EY, IR ER, that is here IR here, and IY EY, IY EY here, and here EB and EB is minus EB and EB is, and IR into IY. Here EB is a common, so minus EB taken outside and remaining is IR plus IY. So we know that IR plus IY plus IB should be 0. So from this equation IR plus IY means the EB goes to right hand side, so that is minus IB. IR plus IY means minus IB. So substituting here, so instead of IR plus IY I am substituting IB minus IB. So minus IB into minus EB means that is plus EB into IB. So total equation W1 plus W2 now becomes IR ER and IY EY, and the last part is minus EB into minus IB means IB into EB. So that is power in the first phase, power in the second phase, power in the third phase. So W1 plus W2, suppose what reading in the W1 and what reading in the W2, we added each other, means we are getting actually the total power in the system. So here we discuss in the unbalanced condition also. So here suppose any one value, suppose IR is changed and IB is changed or EY is changed, no problem, it is adding each other or multiplying each other. So any value, the power is W1 plus W2. Suppose balanced, all are equal also, no problem, W1 plus W2 is the answer. Suppose values are changed, IR, IY, IB is changed, no problem, the total power is W1 plus W2. Similarly ER, EY, EB also changed, the magnitudes are not equal, then also no problem, the total power is W1 plus W2. So under unbalanced condition also just W1 plus W2 is a total power. So this is a under unbalanced condition we are discussed. So W1 plus W2 is a total power absorbed. So this is a 2 wattmeter method under unbalanced condition. So this is a derivation for the 2 wattmeter method. So this is a figure. This is a figure, this is a derivation for 2 wattmeter method, 2 wattmeter method unbalanced load condition. The 2 wattmeter method 3-phase power measurement under balanced load. This topic is very important. Every time the questions are coming. So in this case we are connected 2 wattmeters to measure the 3-phase power. Here W1, that means wattmeter 1, first wattmeter is connected across R phase and the current coil in the R phase and the potential coil across R and B. And the W2, wattmeter 2 connected in the current coil is Y phase and the potential coil is across Y and B. So here the W1 reads the current is IR. The current is IR, current reads is IR, and here the potential difference, this coil is potential difference is connected R to B, so voltage is V, voltage is, the current is IR and voltage is VRB. So we know that VRB means actually VR minus VB. So we have to find out what is the angle difference between VRB and IR also using the vector diagram. Similarly, the second wattmeter reads current is IY and its potential coil is connected across Y and B. So VYB is a voltage across the wattmeter. So VYB means VY minus VB is a potential difference is across the W2. So from the vector diagram we are going to find out what is the angle between the first wattmeter is IR and VRB. For the second wattmeter the angle between IY and VYB. So first we are going to discuss the vector diagram, that is VR, VY and VB under 120 degree apart each other, and its current IR is lagging by 5 degree, just taken lagging condition, IR is lagging by 5 degree from VR, so IR is here. Similarly VY is here, so IY is lagging by 5 degree, so IY is here, so VB is here, so IB is lagging by 5 degree, so IB is here. These are current conditions in the given load. So now we have to find out the voltage across, that means voltage across W1 is VRB, that is VR minus VB. So we have VR but we don't have minus VB. So minus VB, for minus VB we extended VB into minus VB here. So we are getting the vector diagram here. VR and the VB parallelogram method. So VR extended here and VB extended here. So we got VRB here. So VRB comes here. So now we are finding the VRB and IR phase difference. We know that the VR and VY is 120 degree apart, and exactly half of the 120 degree the minus VB is passed. So total this much area is 60 degree. Again VRB is passed the exact middle, so this much area is 30 degree. So we have to calculate the phase difference between VRB and IR. So total is 30 degree here. So 30 minus 5 is the angle difference between 30 minus 5 is the angle difference between VRB and IR. So next we are going to discuss the angle difference between IY and the voltage. Here IY is the current, IY is the current, and voltage is VYB. So VYB means VY minus VB. So already we extended minus VB here. So just find out parallelogram method, VY and minus VB, its parallelogram is this one. So we got the VYB is this one, VYB. So next we are going to find out the angle difference between IY and VYB. So here we know that this much is 60 degree. So VYB exactly middle is passed. So this much angle is 30 degree. So 30 plus 5. Here the angle is 30 plus 5 is the angle difference between VYB and IY. This much is 30 plus 5. So second wattmeter, the angle difference between the how much current and what potential difference across it, the phase difference is 30 plus 5. In the first wattmeter, the phase difference is 30 minus 5. First wattmeter measures VRB and IR. Second wattmeter measures IY and VYB. The angle difference between the current and voltage of these two wattmeter is, first wattmeter is 30 minus 5, second wattmeter is 30 plus 5. So in the next slide we are going to discuss with its derivation. So the W1 carries the current IR, the voltage across it is VRB. So the wattmeter reads the voltage across it and its current and its cosine of the angle between the voltage and the current. So W1 means actually VI cos phi. Here V means VRB, I means IR. Cos, its angle difference is 30 minus 5. This much value the W1 reads. Clear? And the second wattmeter, the voltage across it is VYB and the current is IY. So W2 reads the current IY and voltage VYB and the angle difference is cos 30 plus 5. So this much value reads by W2. So now it is under balanced condition. So everything is under balanced condition, so that we can take it as VRB equal to VYB, because balance condition all the voltages are same and currents are same. So VRB is the line voltages and VYB also line voltage, taking as VL. And balance condition currents also same, so IY equal to IR, taking as IL. So VRB equal to VYB we are denoting by VL and IR equal to IR, and we are denoting it as IL. So W1 reads means VL IL cos minus 5, that means VL means here VRB, IL means IR into cos 30 minus 5, and W2 means VL IL cos 30 plus 5. So now we are going to add these two values, that means W1 plus W2 is the, this one value is the W1 plus W2 value, this is the total power. So while doing the W1 plus W2, here VL IL, here also VL IL, so these are common, so we taking outside, so VL IL is taking outside, and remaining is cos 30 minus 5 plus cos, remaining is cos 30 minus 5, minus 5 and plus cos 30 plus 5. So in this case, here cos 30 minus 5 means cos A minus B. We know that the mathematical formula cos A minus B, here A means 30, B means 5, cos A minus B means cos A cos B plus sin A sin B. Here cos A plus B means cos A cos B minus sin A sin B. Here also A means 30, B means 5. So applying that rule here, so cos A minus B rule, first one, so cos A, that is cos 30, cos B means cos 5, the first part. Next is, here minus means the sign is plus, so sin A is sin 30 and sin 5. The second cos 30 plus 5, that means cos A plus B, so cos A cos B, cos 30 cos 5, the plus for plus, the minus sign, so minus sin A sin B, sin 30 sin 5. So here plus sin 30 sin 5, this value, and minus sin 30 sin 5 cancels each other. So remaining is VLIL into cos 30 cos 5, this value, and plus cos 30 cos 5. So 2 times. So VLIL 2 into cos 30 cos 5. Here cos 30 means we know the value, cos 30 equal to root 3 by 2. Root 3 by 2. So substituting instead of cos 30 root 3 by 2, the 2 and this 2 is cancels, remaining root 3. So root 3 taking this side, so root 3 VLIL cos 5 is the last answer. We know that we already calculated what is power in the 3-phase power is root 3 VLIL cos 5. So W1 plus W2 means root 3 VLIL cos 5, that means total power in the 3-phase circuit. So this is the W1 plus W2 is the total power in the circuit. So this 2 wattmeter method confirms just adding what the reading in the W1 and what's the reading in the W2. Adding these two values, we are getting 3-phase power. So hence the sum of 2 wattmeter readings gives the total power consumption in the 3-phase load. So 2 wattmeter method works both in unbalanced condition also, we discussed earlier, and it works properly in the balanced condition also. Comparing to 3 wattmeter method, 1 wattmeter is reduced, so less number of wattmeter is enough to read accurately the power, and it is easy to calculate also. Only W1 plus W2 gives the total power. So these are the advantages of 2 wattmeter method. Another advantage is connections. So comparing to 3 wattmeter method and 2 wattmeter method, the connections are less, and this one is properly working in the delta connections also. The delta connection 3 wattmeter method is very different, very difficult to connect, but in the delta case the 2 wattmeter method is very easy to connect also. So here instead of star, suppose the delta connections, it is very easy. The delta is like this. So the remaining W1 and W2 connections also remains outside the delta. So it is easy to connections also. So star means the same connection, delta also same connections, no need neutral also. So it is very easy to connection also and very easy to calculate also, and it works both in balanced and the unbalanced condition also. So this method is very popular in the three-phase power measurement. So this method is widely using in the three-phase power measurement. To understand the 2 wattmeter method, we have to know the vector diagram also to identify the angle between line voltage and the current. So in the first wattmeter, the phase difference is the cos -5. In the second wattmeter, the cos +5. So total power is W1 plus W2 is √3 VL IL cos phi. Next is how to calculate power factor by using the 2 wattmeter method power measurement. Using the same values in the W1 and W2, we can calculate the power factor of the load also. So here we know that the W1 value and W2 values, W1 value is VL IL cos 30 minus 5 and W2 is the VL IL cos 30 plus 5. So while adding these two, we got the answer, that is √3 VL IL cos 5. Next, similarly we can find out W1 minus W2 also. So W1 is VL IL cos phi 30 minus 5 minus VL IL cos 30 plus 5. So while doing the derivation, we are cancelling the cos terms, not the sin terms. In the earlier case, we cancelled the sin terms. Here cos terms are cancels each other and remaining only sin terms are remaining. That is 2 sin 30 sin 5. Sin 30 is 1 by 2. So 2 and 2 also cancelled. So remaining VL IL sin 5. So W1 minus W2 is the VL IL sin 5. So now we got 2 equations, that is W1 and W2. W1 is first equation, W1 plus W2 is √3 VL IL cos phi, and W1 minus W2 equal to VL IL sin phi is the second equation. Now dividing second by 1, second equation divided by first equation. The left hand side is W1 minus W2 divided by W1 plus W2, and the right hand side is VL IL sin phi divided by √3 VL IL cos phi. So from this equation we know that sin phi by cos phi is a tan phi. Clear? So we are taking tan phi outside. So taking tan phi outside means this term goes to, and VL IL cancels, only √3 in the denominator is remaining. So only taking tan phi outside means the denominator √3 goes to numerator side in the left hand side. So √3 into W1 minus W2 divided by W1 plus W2 equal to tan phi. So phi equal to tan inverse √3 into W1 minus W2 divided by W1 plus W2. This is a phi. Once we know the phi value, next we can calculate the power factor. Power factor, we know that power factor equal to cos phi. So cos phi equal to the phi value we can insert here. So power factor equal to cos phi. So cos into this much phi equal to, we know that tan inverse √3 into W1 minus W2 divided by W1 plus W2 is a total power factor. So if you know the W1 and W2 value, we can calculate very easily the power factor also. This is another advantages of the 2 wattmeter method. Next is variations in wattmeter readings. So we know that the power factor varies the power reading also. Here phase angle phi, based on the phase angle phi we can discuss the various wattmeter readings under various power factor conditions. So cos phi is the power factor. So from W1 we know the reading. W1 gives the VL IL cos 30 minus phi value, and W2 reads VL IL cos 30 plus phi value under lagging power factor conditions. So first condition here when phi equal to 0, that means cos 0 equal to 1, that means unit power factor is unity. When power factor is 1, what happens in the reading? So W1 equal to VL IL cos 30 minus 0, that means cos 30. W2 also, W2 equal to VL IL cos 30 plus 0, that also cos 30. So W1 and W2 reads same value at this condition. So at power factor is unity or power factor equal to 1 or phi equal to 0, the W1 and W2 reads same value. Suppose we know the VL and IL value, the value should be root 3 by 2 VL IL, because cos 30 is root 3 by 2. So both are gives same positive readings at this unity power factor condition. Next is power factor is 0.5, that means phi equal to at 60 degree, power factor is 0.5. Cos 60 equal to 0.5 or 1 by 2, clear. So in this condition W1 equal to VL IL cos 30 minus 60. So 30 minus 60 means minus 30. In the cos minus 30 or plus 30, it gives positive values only, that is root 3 by 2 VL IL. So at this condition when phi becomes 60 degree, the W1 reads positive value root 3 by 2 VL IL value. It has some value in the W1, but in the W2 case, W2 VL IL cos 30 plus 60. So 30 plus 60 means it becomes 90. So cos 90 is 0. So VL IL into cos 0 means cos 90 is 0. VL IL into 0 means 0 power. So at this condition W1 is read some value and W2 is 0 at the power factor is at 0.5 or phi equal to 60. Only W1 reading is the total power. W2 reads exactly 0 value. Third condition phi equal to 90 degree. So W1 is VL IL cos 30 minus 5 cos 30 minus 90, that is VL IL sin 30. Here 30 minus 90 means 60 minus 60. So that minus 60 we can replace with cos minus 60 equal to sin 30, clear. So that is written here, cos minus 60 replaced with sin 30. So sin 30 is 1 by 2. So 1 by 2 VL IL, that is a W1 reads VL IL sin 30, is 1 by 2 VL IL value. So next is W2 is VL IL cos 30 plus 90, that means 1 cos 120. Cos 120 means that is replaced by sin 30 or cos 120 equal to minus sin 30. So it reads minus VL IL sin 30 or minus 1 by 2 VL IL. So that means both are W1 and W2 both has some reading, but one wattmeter W1 gives positive value and W2 gives negative value. So how to take the negative value means the connections in the W2 wattmeters current coil is interchanged, so that we can take the reading but indicated as minus value. So both are equal values but opposite in sign. So W1 plus W2 is 0. So we know that at cos 90, the cos 90 comes in at pure inductor or pure capacity value. Here we discussing lagging, so inductive. So cos 90 condition means power should be 0. So total power we got 0. W1 plus W2 means it is 0. So under phi equal to 90 condition, power should be 0. But both are read some value in opposite magnitude. So under first condition at cos 0, that means phi equal to 0, both the W1 and W2 are has values, positive values, and both are equal values. And the second, at power factor is off condition, only one wattmeter shows the reading, that is W1 shows the reading, W2 shows the 0 reading. The third condition, whenever the phi equal to 90 or 0 power factor, the total power is 0. W1 and W2 shows the reading but opposite sign, equal magnitude, opposite sign, so total power is 0. So this table gives the conclusion of the variation of power factor. So phi is given the first row 0, 60 degree and 90 degree condition. So cos phi is 401.50. Power factor is 1, power factor is 0.5, power factor is 0 in the third. So in this condition, first condition, both are at power factor is 1 means both are positive and both are equal values. In the 60 degree 0.5 power factor, only one wattmeter shows the reading, positive reading, and another one is 0 reading, W2 is 0. And the third condition, at power factor is 0 power factor, both gives the reading equal magnitude, opposite sign. So W1 equal to W2 but opposite sign, W1 plus W2 is the 0 in the third condition. So conclusion of the variations in the power factor of 2 wattmeter method. Next we are going to discuss how to calculate the reactive volt amperes with the 2 wattmeter method. So we earlier discussed the 2 wattmeter methods, total power is W1 plus W2 and the power factor is cos phi equal to, we calculated using W1 and W2 values. In the power factor calculation, we got tan phi equal to root 3 W1 minus W2 divided by W1 plus W2 value. So using this value, tan phi value, we can draw the triangle because tan phi means opposite side by adjacent side. So here using tan phi equal to opposite side is root 3 W1 minus W2 and the adjacent side is W1 plus W2. So now we know that W1 plus W2 means total power, that is active power. So that root 3 into 1 minus or W1 minus W2 is it should be reactive power. So if you know the W1 and W2 and doing the subtraction W1 minus W2 and multiplying with the root 3, we are getting directly the reactive power, that is kVAR. So if you know the W1 and W2, so just multiply root 3 into W1 minus W2. So here the derivation is given. So derivation given root 3 into W1 minus W2. So we know that W1 value, so W1 value is VLIL cos 30 minus 5 and W2 is V minus VLIL cos 30 minus 5. So VL and IL is taking outside, root 3 into VLIL, and here cos 30 minus 5, again we taken cos A minus B. So equation becomes cos 30 cos 5 plus sin 30 sin 5, and the second part is cos 30 sin 5 cos 30 cos 5 plus sin 30 sin 5. So here this part goes to cancels each other, so remaining only sin 30 sin 5 plus sin 30 sin 5, that means 2 into sin 30 sin 5. So 2 into sin 30 sin 5, here sin 30 we know that 1 by 2, so here sin 30 means 1 by 2, so 1 by 2 means this 2 and this 2 cancels, so only sin 5 is remaining. So root 3 VL IL into sin 5, that is a reactive power kVAR of the load. So if we know the value of W1 W2, so we can calculate directly the reactive power. That means just multiplying the W1 minus W2 into root 3, that is a reactive power. Just adding to W1 plus W2 means active power, and W1 minus W2 into root 3 is the reactive power. This is another advantage of 2 wattmeter method. We can calculate directly the active power and reactive power by using the readings of W1 and W2. So next is 1 wattmeter method. So we discussed 3 wattmeter method of 3-phase power measurement. Next we discussed 2 wattmeter method for 3-phase power measurement. Next we are calculating 1 wattmeter method for 3-phase power measurement. So while discussing these 3 points, we have to, and finally we are going to make the conclusion of which one is best for the calculation, etc. So in this case 1 wattmeter method, the connections are shown in the figure. Here any one phase is connected the current coil, and the potential coil is connected to 2 alternate connection to 2 phases. So in this case, suppose the connection is given to, the potential difference connection is given to first one. So now the wattmeter is connected across R phase and the Y phase. So now this one is act as W1. Clear. Next is we are changing the connections and we are connected to position 2. Now this wattmeter is now connected across R phase and the B phase. This reading gives to W2. Once we know the W1 value and W2 value, so adding these two we will get the total power. So just interchanging the potential difference coil connections, position 1 to position 2, that means one phase to another phase, we will get W1 reading and the W2 reading. Once we know the W1 reading and W2 reading, it is easy to calculate the total power. Total power is W1 plus W2. So this one we are using for both balanced and unbalanced condition. W1 plus W2 is gives the exactly accurate reading for balanced condition and unbalanced condition. So it's a 1 wattmeter method calculation, and the same 1 meter method we can use for balanced condition. Suppose we connected the under balanced condition, suppose it is a star connected, balanced and star or Y connected. So we can connect the wattmeter any one phase, that reading into 3 means we will get 3-phase power, but only under star connected and balanced connection only we can use the wattmeter, 1 wattmeter method, 1 phase and 1 neutral across connection, and multiplying that power into 3 means 3-phase power. But we are actually using W1 plus W2 method for accurate reading. So this is a 1 wattmeter method. So VYB IR cos 90 minus phi, that gives VYB means our line voltage VL, IR means line current IL, VL IL cos 90 minus phi means sin phi. So VL IL sin phi. So we got the reading is W equal to VL IL sin phi. So this is only VL IL sin phi only by using only one wattmeter, but multiplying by root 3 is a reactive volt ampere or kVA reactive power by using only 1 meter. What readings comes in this wattmeter multiplied by root 3 is the total reactive volt ampere. The connection is only current coil is connected any one phase. Here R phase current coil only, the voltage potential coil is connected across to Y and B here. So at this type of connections we can calculate the reactive volt ampere directly. That means what value obtained in the wattmeter multiplied by root 3 gives the total reactive power. That means now becomes root 3 VL IL sin phi multiplying by our root 3. So this is a method for calculating using one wattmeter method. Total power is W1 plus W2 and the reactive power also. So next is need of power factor improvement. So we discussed a lot of conditions with power factor effect. So once the power factor is improved, so that means power factor becomes 1 or nearer to 1, it has or it gives advantages of the some advantages on system. So we are discussing some points here. So first point is reduction in copper losses, hence size of conductor. Suppose the system working under power factor 1 condition or nearer to 1 condition, the total power losses will be reduced, the current carrying also reduced, so copper size also conductor also size is reduced, so copper loss is reduced. Next is efficiency will improve. Third one is cooling in equipments improves. Lower the utility bill. Suppose power factor is 1 means the electricity bill also reduces, because otherwise we are drawing more current but utilizing less power. V I cos phi, here cos phi, suppose cos phi value is 0.5 means how much current we are drawing in voltage divided into 0.5, that means divided by 2. So half of the power only we are actual consuming, so electricity bill goes high. So once the power factor is 1 means V voltage current into 1 means the full power we are utilizing, so we are getting less bill, and it gives voltage regulation improves also. Suppose power factor reduces means current increases, once current increases simultaneously the voltage decreases, the voltage regulations is affected. So once the power factor is improved, the voltage regulation also improved, constant voltage will get. Increase system capacity also increased, and less total plant kVA for the same kW working power. So all the generating stations and the transformers are rated in kVA. So kVA, the same working kW, the less kVA is required under power factor improved condition. So these are the need of power factor improvement. Next we are going to discuss the what are the equipments are using for the improving power factor. Here synchronous motor. Here synchronous motor means one different motor. That means we are supplying the stator 3-phase supply, and rotor is rotating, but rotor also we are supplying DC power, so that motor is becomes synchronous motor. That means once we connected the 3-phase power to the stator winding, In the stator winding, a magnetic field is rotating, or rotating magnetic field is produced. That speed is depends upon the frequency and the number of poles the speed is designed. So while connecting the DC power to the rotor becomes a magnet north and south, so that it catches, so that the magnets catches each other, and the rotor also rotating at the speed of the rotating magnetic field. That speed is called as synchronous speed. So that totally the motor also called as synchronous speed motors or synchronous motor. So once we increasing the DC supply, or the DC supply is called as exciter. So over excitation condition, the synchronous motor is behaves a leading condition, so it cancels the lagging current. So totally power factor is increasing the system. So this power factor increasing due to the over excitation of the synchronous motor. So it is neutralizing the lagging power factor, so lagging current, and it provides leading condition. So lagging and leading, and it neutralize each other, so that the current, the net current becomes nearer to zero phase difference to the voltage. So that the power factor nearer to 1, or we can make it as exactly 1 also by using synchronous motor. So this type of motor is called as synchronous condenser or synchronous capacitor also. Next is static capacitor. I think you know all are know the static capacitor. This is just capacitor connected to the appliances. So capacitor gives the leading current. So almost all our appliances has lagging condition current. So suppose we are connecting a parallel capacitor, the capacitor current and the lagging load current are cancels each other, so that the net current, the capacitor current plus the lagging current equal to, it is very nearer to the zero phase difference, so that the power factor is improved. So in the motor or in the fan also, or any lagging or induction motor etc., the capacitor is connected to improve the power factor. Next is phase advancers. This one is one special equipment which is works in induction motors only, because induction motors are the main equipments that are produces always very less power factor or very poor power factor. To improve the power factor, we have to connect the static capacitors, or we can say one equipment phase advancer. This phase advancer is connected or the same shaft of the rotor of the induction motor. Only the special induction motors only comes with phase advancer. Normal induction motors are not comes with phase advancer. Only the special induction motors are comes with phase advancer. So this one gives over excitation to the rotor, so that the total power factor is improved in the induction motor. So these three items are mainly using for power factor correction: synchronous motors or synchronous condenser, static capacitors and phase advancers. Static capacitors we can use for all the equipments, and synchronous motors and are using for industry uses, and the phase advancer also using for the also using industrial purpose only. Thank you.